Good day to you all. Today we are going to start a new course on the principles and the practices of process equipment and plant design. The course will be taken jointly by Professor Gargi and myself, S. Ray, and today we have the first lecture, which is on the introduction to the topic. If you look at the topic, there are a few things that we definitely have to appreciate right at the beginning, that we are going to talk about the principles as well as the practices, and three more keywords are also there. The first is the process, the second is the equipment, and third is the plant and the plant's design. So this is what we start off. The first question that must be answered in this particular state is, what exactly is a process? And since we are talking about a process design which definitely is pertinent to industry and industrial processes, we would like also to have a definition of the industrial process. After all, it's a part of engineering. So a question should also be clear in our mind that what we really mean by engineering design. We need to talk about its steps in achieving a final engineering design and look at the deliverables to be provided from this course. If we talk about a process is always with a function, a very specific function. For example, if you are talking about a material which has to be heated, it could be a kerosene stream of maybe 70 meter cube per hour, available at a temperature of 30 degrees centigrade, to be used as a solvent and is to be used after heating it to a temperature of about 85. So the process is, in this particular case, heating of a particular liquid stream, which is kerosene, from an initial to a final temperature. We definitely also have the definition of process in terms of unit operations and unit processes. The conventional definition of unit processes says that it involves a step of reaction, whereas it's only the physical process in case of unit operations. For example, if you are talking about a physical process of mixing as an unit operation, where we mix several streams to achieve homogeneity, yes, it's a process definitely which does not involve any chemical reaction, but involves physical process of mixing. Similarly, if we talk about a separation of a multi-component materials stream, for example, the separation could be based on various different things. It could be, if it's a solid stream, it could be based on size, it could be based on various other properties like magnetic nature or all, or it could even be a homogeneous mixture of different hydrocarbons being separated either by the chromatographic process in the industrial scale or even by distillation. We talk about reactions, which is also a process. It basically involves chemical conversion of the reactor feed to products, and quite naturally, in almost all cases of chemical reaction, you will always have a separation step for the product, so that you can sell the produce that you have got out of the reaction after separating it to the required purity. Now, with this in our mind, I believe we have a fair description with us what exactly is a process. The next point which comes into our mind is basically what's an industrial process. Yes, we have several processes in our laboratories. We definitely will be calling a process an industrial process when it has got some commercial manifestation. For example, it converts feed material to useful products, a single or a multiple number of products of a desired quality in commercial scale. Normally, that's the conventional idea about an industrial process. The steps involved, obviously, it needs to be technically viable, safe and economic. So one major feature of an industrial process is the steps are feasible or viable and economic, and they definitely have to adhere to the safety standards. If you look at different types of processes and their classification, obviously the simplest classification would be a simple process and a complex process. The process can also be performed as a batch, or it could be a continuous process also. There are several cases of combination of batch and continuous, and definitely there are certain advantages and disadvantages of each. In case of a batch, normally what we do is we have a set of equipment, we feed it first with the set of the feeding material. It could be the reactants in case of a reaction batch, or it could be some feed batch in case of some sort of physical processing like distillation. It could be crushing, grinding, anything like that, and we perform the operation. At the end of the operation or the end of the batch, naturally what we do is we take out the material and go send it for further processing if required. So, one thing is true, that in case of any batch process there will be startups and shutdowns, and you also have to remember that in any batch operation the entire feed material of the batch is normally fed to the batch equipment in one shot. So, if I have a processing system for a 10 ton per day, and if I decide that I will be doing it in a batch, my batch should be capable of holding all the 10 tons of material together. It is also possible that I have the 10 ton per day capacity broken into maybe 3 shifts, roughly about 3.3 tons per batch, and we have a set of different equipment. But one thing is true, that compared to the continuous processes, the batches will have several startups and shutdown phases, and naturally in between will be the batch operation stage. And in case of, compared to this, in case of continuous plants, what we definitely will be having is, you do not have such startups and shutdowns frequently. What you have instead is, you have a startup, you operate your plant continuously as long as you require it to operate, and then shut it down. So, this gives us a few interesting features of the batch and the continuous. The first thing, since the entire batch feed has to be held in the same equipment as the batch starts, the batch equipment for the same capacity per day will be much larger in size. In case of continuous plant, for example, if I am processing 10 tons per day, the capacity of processing will be 10 divided by 24 hours, roughly around maybe slightly less than 0.5 tons per hour. So, quite naturally at a time inside I will be having a much smaller quantity of hold up in case of batch, in case of continuous equipment, and my process equipment size is going to be much smaller. So, one thing is absolutely clear at this particular point, that batches will have several startups and shutdowns, continuous plants will have much less number of startups and shutdowns. The batch equipment size is supposed to be much higher as compared to the continuous plant, and there are other features also which makes at times the batch processing more advantageous. For example, if you are processing something in a batch and something goes wrong, it is only the material inside the batch which is lost with respect to quality. That is what I am talking about. That means in my batch processing, the maximum amount of loss from a batch is the batch size. That means if I lose a particular batch in the previous example which I gave of 10 ton per day, I will be losing about 3.5 tons of material in off quality material, which I can correct later on. But at the same time, I have more ways of concentrating on the processing. I can more precisely look at the temperature and pressure conditions of every batch. In case of a continuous plant, definitely we would like to monitor the temperature and pressure or other process conditions, but at the same time I would also like to have that the I'd like to say here that in case of continuous processing, the material that I produce right now goes to the storage and mixes normally with the rest of the material. So there is a chance that if I am sending it to a particular tank, possibly my entire tank will be going off if I have something wrong in my continuous processing. So these are basically the basic differences or merits and demerits of batch. And there is one more demerit which is written in the slide itself. That means, since you do not have many number of shutdowns and startups in case of continuous processing, your energy requirement, which is spent a lot in the startup and shutdowns, is going to be much less in case of continuous processes, and it's going to be higher in case of batch. So with this, what we do is we look at basically the characteristics, advantages, limitations, and what are common in the batch and continuous things. The first thing, in case of batch, we find that it's a bigger equipment that's required. You can have a greater control on the process. You definitely do have more flexibility, because you can use the same set of equipment for producing different quality of material by just altering either the processing time or slightly tuning the temperature, pressure, flow and level and the processing mode. The product value normally, if it is high, the batch extra spent money on the batch process usually pays off. In case of continuous processing, you definitely do have a smaller equipment. You have a higher processing capacity for the same equipment size, and that's basically a rewording of what I have just now said. If you are talking about the advantages of batch, we definitely will prefer it for low production capacity, because if we really want to have a large batch, our equipment size has to be huge. Whenever we require a stricter control, we usually prefer a batch. For example, if we really want to go for a high product purity, for example, in case of pharmaceutical products which require a very high standard of quality, you usually go for batch. You also get greater flexibility in processing of batches. Continuous usually is it's an economic option and has high productivity. There are limitations of batch. For example, two things. The first thing is it is expensive in a relative scale of cost, and its productivity per unit volume of the equipment is low compared to the continuous processes. Batch processing definitely are usually for more expensive material. That's what you find in the fine chemical industry as well as the pharmaceutical industry, whereas usually you will find the large industries or the large scale production facilities in fertilizers, refineries, petrochemicals, they normally will be using continuous processes. We had another demarcation, the simple process and a more complex process. Usually, if I have a single step of processing, for example, I am going to distill a mixture of benzene and toluene into some purity of benzene and some purity of toluene. It is a very simple process and it involves a single equipment. So, in case of simple process, possibly we will be defining a simple process by such processes where we usually have a single unit operation or a unit process. But one thing we must remember, there could be certain auxiliary processes which could be necessary in order to execute this particular step. One such example is, yes, we have a distillation column, but a distillation column is just not a standalone thing. We need to have pumps, we need to have condensers, we need to have storages and similar auxiliary facilities. We need to have a furnace possibly or a heat exchanger to supply heat to the distillation process. Certain example processes are here. One is heating of a particular stream, the example which I gave of heating of a kerosene stream from 30 to 70 degrees centigrade earlier. We sieve for separating solids according to the size. We receive naphtha from the bath tankers to the shore tanks and for transportation to a petrochemical plant few kilometers away. Yes, that is also a process. Removal of hydrocarbon solvent vapor, separation of a mixture of benzene and toluene, the example which I just gave, drying of compressed air for supply to instruments. Now, since all of these are processes and all of these processes work around specific steps or specific equipment, let us try to identify the different, equipment and auxiliary equipment involved. The first thing is heating of a stream. The major equipment in this particular case could be furnace, or it could be a heat exchanger also. In order that the stream is flowing, we got to have auxiliary equipment. For example, we need to have the pumps and we need to have the piping. So, you definitely will be appreciating at this particular point that your process will consist of equipment as well as auxiliary equipment. The sieving for the separation of solids perhaps will involve a trommel, but it will also involve certain bins for storage. Receiving for naphtha will require pump, it will involve pipeline, and it will also have a lot of instrumentation involved. Removal of hydrocarbon solvent vapor possibly will be done by the process of adsorption. Possibly you will be using a carbon molecular sieve or charcoal, whatever is your adsorption material. But at the same time, you got to make the material flow. So, you need to have blowers in place. The separation of a mixture of benzene and toluene could be done very well by distillation. But you will definitely be requiring certain other things which I have mentioned. You require pumps, you require heat exchangers. The drying of compressed gas for the supply to the instruments normally involves adsorption. But you will be requiring compressors and you will be requiring filters, and you definitely will be involving piping network also. So, we move forward now. We come to the complex processes. The complex processes will normally be constituting of several simpler processes. You will have such simpler processes involving reaction. It could be a separation process also. The separation process could be distillation, extraction, absorption, drying, filtration, and many others. You may definitely get involved in different types of unit operations or unit processes, as we have mentioned, and there could be combinations of these as well. I will give you certain examples. The first example is that of an effluent treatment plant. Normally, in any particular process plant, there will be an effluent which will be constituting of different pollutants, which require separate treatments. Some require adsorption, some require skimming, some require some sort of chemical treatment in order to get rid of those. So, quite expectedly, such effluent treatment plants are complex processes consisting of different types of treatments. If you look at a coke oven plant, the plant is for mainly production of different grades of coke, and it also produces byproducts starting from coal. So, it is not just the process where you have the coke oven itself. there is a lot of other equipment and other processes which are associated. So, all individual such processes may be simple processes, but the overall process naturally is a complex process. Air separation plant is also another example where you compress air and distill the air after it liquefies. Similarly, the example of alcohol distillery, the example of petroleum refinery, all these are different complex processes. In case of refining, the major process is that of distillation. Crude distillation is the first step in any refining process. But apart from this, you have other processes which could be cracking of hydrocarbon, hydrotreatment to remove certain impurities, and blending of streams. So, all these together makes the complex process. We have an example here. We have an example in the sense what we have here is this. The first unit is the atmospheric distillation column, which is here. It produces gas, it goes into the gas processing section, it goes into treaters, it produces LPG and butanes. You have a light naphtha stream which goes for hydrotreatment, it goes for isomerization, and it produces isomerate, which is also a product and goes into gasoline blending. Similarly, what I would like to say is there are different blocks here. In fact, though we have just attempted here to represent the entire processing of the refinery on a single sheet, actually each of the blocks which has been placed here are rather complex processes, and the entire thing leads to the integrated plant for manufacturing petroleum products. This is the petroleum refinery example. For example, if we look at the atmospheric distillation unit, the vacuum distillation unit, these two are the major distillation units here. Well, there are other subunits within these boxes which also will be involving the process of distillation, and each of these are complex processes, and the entire thing is often called a refinery complex. So, we have an idea at this particular point to say we have very simple processes or simple processes, we have more complex processes, and we have large complexes like the refinery complex or the petrochemical complex or the fertilizer complex, which consists of several plants intertwined together. So, we have some idea about the plant. What we do now is we talk about the engineering design or the industrial process design. The basic difference in case of engineering is it's not just science. It also involves a good amount of economics. So, what we look for in an engineering design solution or an industrial process design, it is not just the scientific solution. It is not just the scientific solution that we are looking for. The solution definitely must achieve the functional goal. We have talked about the functional goal in different examples earlier, but it must be achieved economically. So, in essence, if we are talking of engineering design, there are two features. The functional goal must be achieved and it has to be achieved economically. It is obvious that if in order to achieve anything in reality, it must have a scientific solution. So, definitely the solution is a solution as long as it is based on the fundamentals, it serves the functionality and it works economically. We definitely have to talk about, whenever we talk about design, very often we hear the term optimum design. By optimum, normally we mean we gain one way and we lose other way, and there is a balance. So, basically in case of optimum design, what we look for, is a balance of improved performance and increased cost. Yes, we can improve the performance even more by investing more, but by increasing the cost, but there has to be a balance. Now, in order to obtain the optimum design, it is essential for us that we achieve it quickly. Quite often there are quite a few thumb rules or heuristics. These are basically the qualitative considerations. The hypothetical, or rather the theoretical heuristics, can lead to near optimum, but if you really have to achieve the exact optimum or a working optimum about which you are confident, only the qualitative considerations do not help. One got to have quantitative considerations or the mathematical optimization technique also resorted to. So, you definitely will be using heuristics in your design, and you will also be using certain mathematical techniques to optimize your design. So, both are required. Thank you. I think from here we start off in the next class.